but I just can't. I can't figure out how to tell the registrar. Basically, they're concerned about D's and F's, I think. So I don't know. I'll figure something out. So photons. We said electromagnetic radiation. All those cousins travel in waves. This is my wave. Okay. The less energetic, this is my radio waves over here. The less energetic, the longer the wavelength. The more energetic, the shorter the wavelength. The other thing that they travel in waves, but they also travel in these little packets of energy called photons. It's just a wonderful thing. Okay, so when we talk about telescopes, sometimes we call them photon buckets because like a bucket collects like rainwater. A mirror or a lens in the telescope will collect photons so we can kind of gather them together and see them concentrated. This is the artist's rendition of the Hubble Space Telescope. Whenever I stand up here and go like this is my solar panels. So you can kind of see the solar panels here on the telescope. Okay. Now, Hubble Space Telescope orbits the Earth. I didn't bring in my Earth, but it orbits actually from pole to pole, not around the equator. It takes about an hour and a half to make one pass. The Hubble Space Telescope. There's awesome stories about the Hubble Space Telescope. But it's actually equipped to do all sorts of neat little things and going to have to be decommissioned here in the next, I don't know, 2-3 years. And we've got something in the wings to try to help it. But as you might imagine, a telescope that orbits the Earth, it does a lot of good things in that, for instance, we don't have the Earth's atmosphere to worry about. So that's probably the biggest thing why we have a telescope orbiting the Earth. And we have all sorts of telescopes that do that, but HST stands for Hubble Space Telescope. So what do these light buckets do? And we're going to see there's two types of telescopes, but they actually, when we look through the eyepiece of a telescope, or no eyepiece, just imaging, we are able to see things more brightly, see the details of things, and see things at longer distances. So the two types of telescopes, what we're going to go into the chem lab here in a minute, are ones that use ones that use mirrors. Okay, and they both start with letter R, which drives me nuts. So the mirrors ones, of course, when you look in the mirror, you see reflection. So there would be reflectors or reflecting telescopes. And then the other ones use lenses to collect light. Okay, so these next few slides kind of convince you that the bigger your telescope, kind of the rounder, the bigger the diameter of your collecting device, the better the telescope. And you're like, duh, but more expensive? Yeah. I don't have any key suggestions. Sometimes people come to me like, this is nice, what kind of telescope should I get? Well, it depends. And you can ask us several questions. But as far as the problem is, I should say, you kind of get what you pay for with telescopes. So if you get an inexpensive telescope that still looks pretty big, probably it's inexpensive because its optics, what we call its optics, are cheap. Okay, they have imperfections in them that will kind of give you a bad view. So that doesn't mean it's not worth it. It just means you get what you pay for. So the bigger the better. So left to right, you're looking at who in here saw Andromeda Galaxy. Yeah, I think, if you were out, Andromeda Galaxy. Andromeda Galaxy is on a collision course to the Milky Way galaxy. And the Andromeda Galaxy has two pesky little companion galaxies. You can kind of see them here. But from left to right, the left one is the smaller diameter, and the right one is the larger diameter. Okay? So how would you describe these two?
The one with the bigger diameter is definitely closer.
Mm-hmm. Well, it looks closer. But it kind of looks like the field of view, like this is one of the companion galaxies. It's over here, but like the companion galaxy. How would you compare those two?
I guess it's kind of stretched a little bit more.
It's stretched. It's stretched. It's larger. It's brighter. Yeah, but you figure, very good. So you get more photons. You get more photons if you get a bigger bucket, basically. So to brighten, the second one is we use telescopes so we can see teeny tiny details. Okay, see details versus kind of being smeared out. I mentioned that I'm trying to kind of make sure I hit these hot spots. So this is one of the hot spots. It's called angular resolution. How much detail, how crisp it is. basically the smaller, have you ever heard as fine as frog hair? I don't know, our pastor used to use it all the time. So that just means it's very thin, okay? It's fine as frog hair. That just means that your angle is very small. You can see all sorts of detail. So angular resolution says how much detail you can see. The smaller the angle, the better. So I've got some examples here. Again, we're looking at Andromeda. It looks a little fuzzy here, right? And here it looks crisper. So this actually, what I call it, angular resolution. The angular resolution over here on the right is better than angular resolution on the left. And to me, the whole fuzziness of the left one versus the crispness of the right one, I feel like I'm kind of doing an eye doctor exam. Which one looks crisper, okay? Hopefully you say the one on the right. To me, the fact that they're similar brightnesses, probably they have similar diameters, it's probably just kind of optics. All right, so Orion. Now you can't see it very good, but Orion has kind of 4 corner stars. 1, 2, 3, 4. 4 corner stars. This is what we call the sword, and there's 3 stars here we call the belt. So A here, I'm going to show you A, B, and C. A is actually invisible light. Now, I already told you that those cousins here on Earth, we look at things in the sky with different wavelengths. So that's visible light. This is X-rays. B is X-rays. You can kind of see some more detail that you didn't see before. And again, if you know what you're looking at, you're like, oh, I know what those X-rays are for. This says that hot stars. My favorite one, though, is this one. So visible X-rays, check that out. Whoa, that's kind of freaky. So those are the same stars, but looking for infrared. And we kind of talked about infrared is thermal energy. Infrared is heat. Got some hot spots in Orion? Yeah. In fact, one of the hot spots, bless you, if we end up and we really might go ahead and get out telescopes, even though it's going to be kind of cold in a few weeks, and see Orion, because this is what we call the sword region. So there's a sword here, but you can see what the sword looks like invisible. Nothing in really X-rays, okay? But that's a hot spot. All sorts of baby stars are being born right there. That's why it's so hot. So I brought a prop here that I'm gonna pull out, but this, excuse me, so there's 2 types of telescopes. I'm gonna test you on this on your test on Wednesday. 2 types of telescopes. Well, they both gather light. One gathers light with lenses, and one gathers light with mirrors. This is a lens. This totally reminds me, if you've ever taken a magnifying glass and the sun is shining, and you kind of move that magnifying glass up and down, and you're trying to kind of get a hot spot here, you can actually start a fire. If you get the light concentrated just right. You can also kill ants, which I don't recommend. So when you do this, actually what you're trying to do is kind of adjust what we say the focal length. So the light comes in and it's gathered to a point, and you're trying to get that point just right there, okay, to the ground. So that's what our telescopes do. In a minute, I'm going to show you a refracting telescope. My telescope, my go-to telescope, that's a refracting telescope. My big one, my long one. Okay, so it has a lens on the end. Light comes to a focal point. It's kind of unpacked through what I say the eyepiece. The other type is a reflecting telescope. So we have some different configurations with reflecting telescopes, but what they all do is have a big old mirror. Oh, wait a minute, this is a refracting telescope. Okay, so this is a reflecting telescope, otherwise called a reflector reflecting telescope. So this has a mirror at the back, okay, and there's different designs, but the mirror is at the base, so light comes in your tube, okay, it comes here and it goes back to a focal point. So the shape here has to be what we call concave instead of convex. So there's different ways to take, do you see where what these all have in common is they have a big old mirror at the base. And we're gonna see that. I kept the one I had out last Tuesday night just to show you. So before we go into the other room, go ahead and pause this. Here's my little, I know, right? I think that's a Mozart piece. Mozart, as in Mozart. So what do you think? Mirror? Looks like a mirror? So actually, this is prepping for a telescope. The bigger the better, right? Right. And what we're going to see actually is most of our humongous telescopes are mirror telescopes, reflecting telescopes.
So how does that work? Like, where do you look at?
Well, it's not done yet. See, he's still working on it. So it will be just like we saw, you know, how we had the light. Well, we had the Dobsonian had the mirror back here, and we looked through the eyepiece right here. So this probably is one where it's the light is going to come to a focal point, and they probably won't have an eyepiece. Sometimes they actually have a person sits there because it's so humongous. Sometimes they have like just a camera that gathers the photons in front of the image. But that's a lot of light gathering. Yeah, 8 meters. 5 meters, 8 meters. Okay, big. Okay, this one actually, you asked how that works. So in the telescopes that I showed you, I've got what's called an optical tube. Now the optical tube doesn't do anything, right? It just kind of is a way to hold the mirror or the lens. Okay, this actually, here's the optical tube here. There is no optical tube. It's just like this kind of open truss. Isn't that fun? Why not? It doesn't do anything. I'm kind of guessing, I'm not sure. Yeah, this looks like it's in a dome. Can you see a slit? I'll show you the slit right here.
Sorry, you're right. I'm sorry, you're right. I'm sorry.
Okay, here's the slit right here. The slit opens up and this dome moves around. So, here's another one. Can you kind of see the segments here? Kind of looks like a honeycomb, like bees honeycomb. These are like 6-sided segmented mirrors. Be like, well, segmenting them, are you sure that's what you want to do? Because won't that interfere with the light coming in and it going back to a focal point for the reflecting? But no, it works out well. And I'll show you why we kind of like those little segments better. This one is another refracting telescope. So if it's a refracting telescope, it's got to have a lens. So here's the lens up here. The lens actually is 40 inches. So here's a yardstick-ish. So you're looking 36. So about 4 inches beyond that. That's how big the diameter of the lens is.
Wow.
Yeah.
That's too big. They spent all that money for it.
It's got historic, I'm pretty sure they recently closed this observatory. But it's got historic purposes. So a refracting telescope has to have the lens at the end of the telescope and it comes back to a focal point when you look through an eyepiece. So you can kind of see, so this would be where we have the eyepieces right here. And you can see the dome. This kind of reminds me, it's a lot larger than the one at the Whitty Observatory, which I hope everybody gets to that observatory. That's by Burlington. But it's kind of got that white dome. It's got a slit and the dome kind of moves around. The slit, of course, is open. So it can just get the starlight or a planet light or whatever. All right, here we go. Where is this one? Chile, right? European Southern Observatory's very large telescope. I was going to ask this in the form of a question, but I don't know how to ask in the form of a question. The thing is about the time you find a nice dark place where nobody is, because you can't have any light pollution to get your best viewing, what happens? People start encroaching. That city that was farthest or closest to you starts getting larger, and it kind of bumps up against your dark skies. So I think anymore, when people invest this much money in a telescope, they're a little more careful about, zoning, right? Things with lots of light can't come near. But this is quite common. It's a complex, so you can kind of see these maybe 4 different buildings. Okay, so they would house an assortment of telescopes. This one is currently under construction. Just humongous. It's kind of showing you next to Coliseum. So this one's coming up. So they both start with the letter A. The only one I have on your review sheet is this one, adaptive optics. We have active optics and adaptive optics. They try to use, but I'm only going to kind of quiz you on the test about adaptive optics. They're similar, but what adaptive optics does, and we'll talk more about twinkling, but what adaptive optics does is, so say this is my telescope. This is my telescope, right? But this, sorry to say telescope, well, okay. This is my mirror. That's part of my telescope, okay? But it's a fancy mirror, one that's segmented. Remember we saw one that had like those 6-sided pieces of glass that made my big old mirror down here? It's segmented so it actually can kind of change its shape a little bit, okay? And then this actually is just a beam of light, okay? Beam of light going out. So basically, we send a beam of light out to kind of test the atmosphere. We're going to talk about twinkle, twinkle, little star, because the stars twinkle, and the twinkling actually can give you problems trying to see a still image. It messes you up. So what this beam of light does is it says, oh, what kind of twinkling we have going on, which is just a function of like what the atmosphere is doing. And so based upon what this beam does or doesn't do, this mirror will reshape itself. Isn't that cool? It's been around for a long time, I guess, but that's called adaptive. Get it? Adapt. It adapts for the Earth's atmosphere. Adaptive optics. I think that is so cool. Active optics, if you read the description, it's a little bit different. It's not segmented, so it doesn't change the shape, but it changes the whole angle of the mirror. All right, so this is Jupiter. Maybe like you haven't seen Jupiter before. And this is from not the Hubble Space Telescope, which takes great images, but remember the Hubble Space Telescope is outside of the Earth's atmosphere, but this is through the Earth's atmosphere using adaptive optics. I think it's kind of dark. I think they could have lightened it up a little bit. So if you, the most recent cameras that I've gotten have this like technology in them to take pictures. Actually, I'm pretty sure if you have a DSLR, I don't know if you're familiar with a type of camera, it uses a chip instead of, it just uses a chip to get the image, and that's what these are, CCDs. More chips. All right. So the other day, remember we've been talking about the cousins just a minute ago. I kind of said short wavelengths here, long wavelengths over here. The problem with long wavelengths coming from outer space or whatever is they're so darn long that if you try to kind of take those long wavelengths, put them through your normal telescope, it doesn't work. It just doesn't work. So I'll talk more about that. But this is kind of a funny story, and we might actually talk more about this when we talk about our galaxy. But there were two dudes, and actually there were a couple other people in a different country that were actually working for Mont Bell, I think. And they were trying to isolate some static that was coming from the sky. And as it turns out, that static wasn't coming from Earth's sky. That static was coming from beyond Earth's atmosphere. And actually, that was the beginning of looking at stuff in the universe using radio telescopes. So what was pesky was actually amazingly awesome. So here's our cousins, and I should see these on your cheat sheet. It's not really cheating, on Wednesday. But you can kind of see the long wavelengths, radio, microwaves, infrared, visible. Of course, visible goes Roy G. Biv. You can kind of see it going up there. Then after violet, we have ultraviolet, which makes sense, X-rays and gamma rays. So with regard to these long wavelengths, that's what I started to say. We can't use normal telescopes, but instead we kind of use an assortment of little dishes that come together and work together. Okay. So this is one of your terms called interferometry. Interferometry, think of that as multiple telescopes coming together to make a single image. And the reason we need to use interferometry with radio signals is because they're so long. The wavelengths are so long. Okay, so interferometry.
What are those guys?
Out in the desert is a good place to have some flexibility you need to with interferometry. Like in our southwest United States, there are actually telescopes, you're going to see here in a minute what I mean by little dishes for telescopes that are on train tracks to kind of move them around where you want them to go. So here we go. Do you see what I mean by, like, I'll use the word army, like an army of army of little dishes? Don't these look like satellite dishes?
Yeah, they do.
They do, yeah. So these would be dishes that are looking for the radio signals from a common point, but that wavelength is so large that they have to spread out. You can't capture something that big unless you have something big. Okay. All right. So we have visible light here. What planet is that? Saturn. Yep, you're going to be able to look at planets and say what they are. Saturn, yep. And this is Saturn, though, and looking at the radio energy it's sending out. That's kind of cool. This is a radio image of a pair of galaxies that are interacting. Okay. So another radio telescope. Beautiful. This kind of reminds me of, have you ever seen the movie Contact? Yeah, long old movie.
Nice.
Not yet. All right. Radar. Yeah, actually, this one was in the news. Puerto Rico had some awesome observatories, and I don't know if they're going to get back up and running again. I mentioned the Hubble Space Telescope that currently orbits the Earth about every 90 minutes, pole to pole, the Hubble Space Telescope. It's going to be decommissioned, and this is the one that we have going up to replace it. Check out these people in their white suits, okay? They're clean suits. Don't want to have any little germs on their stuff. Again, an artist rendition of a coming telescope. So twinkling. Twinkling basically is what I was talking about a minute ago, where we send up a beam of light and see how it's kind of scattered because of twinkling. I meant to, but didn't bring it in. You're just going to have to imagine that, for instance, this is a candle, okay? And I light my candle, so I have flame here, and you kind of go at different angles. Have you ever seen it where actually not in the flame, but around the flame, when you look at objects, they look like they're kind of shimmery, kind of. Yeah. That's actually twinkling. And the reason is because the heat from the flame is actually changing kind of how the light behaves. So twinkling in our atmosphere is due to actually blobs of air that are moving, and these blobs of air at different temperatures. Do we have any wind the other day?
A little bit.
Oh, we can move.
Oh, I wouldn't. Yeah, I wouldn't have sound like that.
Yeah, like it was it Saturday?
Well,
Friday.
I mean,
Saturday.
well, back at home, like back in my hometown in Indianapolis, I saw it on Snapchat and stuff that are like the street lights, you know, the lights from yellow, blue, I mean, I can't even say green, yellow, whatever, they fell down, like they were hanging down to the ground.
Not good.
Yeah, and then like a stop sign, and like it was a lot of wind, they said.
That's not good. But we get the wind. I mentioned that because we get the wind when we have like warm, and the next day is cold, the next day is warm, the next day is cold. That's going to create wind all the time. So we kind of have that in our atmosphere doing that. So when the skies are steady, what we say in astronomy is that the viewing is good or the seeing is good. Okay, and why would they be steady? Well, if you look at what's happening in the upper atmosphere, you don't have alternating blobs of warm, cold. Okay, I know it's really cold, but like actually December, and the observatory closes. We aren't open in December, and then we reopen, I think, in April. But the cold skies can give you some awesome viewing. So left to right, this one actually is the same view of stars. This one is if you were to look at those stars from a telescope that's going through the Earth's atmosphere. This one on the right was the same field taken from the telescope that's beyond the Earth's atmosphere, the Hubble Space Telescope. All right. is that the last term?
Yeah, 21.
Good. So we'll finish up with a few slides here. One thing I'm not going to test you over this semester, but it's really exciting, I think. It's an important aspect of our Earth, let alone astronomy. But you figure Earth, of course, has an atmosphere because Earth has a certain mass and it keeps the little nitrogen, oxygen, then carbon dioxide and water molecules, a gas, kind of where they are. But Earth's atmosphere then also has kind of an interaction with incoming cousins. Up here, you know, I could have gamma rays over here, radio waves over here, all 7 of them. Depending upon the energy, Earth's atmosphere will have a different sort of play. Okay? So here's what that play looks like. If you look across the top here, we have gamma rays over here on the left, and we have radio waves over here on the far right. So they're all the different cousins. Now, the length of this kind of little bar at that energy says how much of that energy can get through. So, for instance, if we're looking at visible light right here, look, it goes all the way through. Okay? Up here, it gets blocked. It gets about this far. Okay? This is even blocked more. Okay? So when it gets all the way through, that means that that particular cousin, that particular energy can get through. And I mentioned it's really important because look at the gamma rays and X-rays and ultraviolet.
Oh, short.
They're short, so they don't get all the way through Earth's atmosphere. This actually reminds me of, have you heard the whole airplane travel? And are we exposing ourselves to more radiation if we're traveling in the upper elevations? Maybe. I'm not quite sure where that is, but, oh, see the show plane. Yeah. So if that plane, if this is drawn to scale, that plane should be fine. Because this stuff actually kills cells, mutates cells, causes cancer.
You said what? New cells?
Mutates cells.
Oh,
Kills, mutates cells.
2 heads.
What's that? Yeah.
So grow 2 heads.
But does some of the UV get through?
A little bit.
A little bit. So there's NOAA doing their thing. This is the same guy, invisible, and this is him in infrared. So isn't that cool? Because of course you can't see his hands through the sac in the visible, but you can see his hands through the sac in infrared.
Because they're hot, right?
Yeah, because they're hot. So infrared and heat are the same thing. So here we have some different nebula. Aren't these pretty? All a nebula is, these are planetary nebula. Wait, no, they aren't. This isn't planetary nebula. But a nebula is a chunk of gas. Solar nebula, well, it's a solar nebula. That's a term on there. What is a solar nebula? Just a giant cloud that our sun and planets came from, exactly. These happen to be nebulas that are glowing. These were taken from the Spitzer Space Telescope that also orbits the Earth. But what I know about the Spitzer is it's not taking visible images. It's actually taking infrared images. This is cool. Those are not stars. Those are actually galaxies. Yeah.
So them are all, let me show you. That's a dumb question.
Not that. They're galaxies.
No, yeah.
Yeah. Left to right, what planet is it? Saturn, very good. We have Earth-based, and then we have adaptive optics on the Earth, and this is the Hubble. Chandra X-ray telescope. And this is what our observable universe looks like in X-rays.
What the hours?
Mm-hmm. It's from, we're kind of in the middle, and that's the stuff around us.
We have a big red egg around this.
Well, it kind of goes to the edge. The reason we can't see past it is at some point, how do we say this? The edge of our observable universe. If we were to move, our egg would be more over here. Do you know what I mean? We just have a limit to what we can see. And that's because light from the Big Bang can't get to us because it hasn't been shining that long. It's hard to describe. As you can see. Yeah. Well, good. Well, we got through like 10 billion slides. So, any questions? keep those labs coming if you don't already have 2. Because I'm gonna be done for the day, guys. Any questions? Whee! Yeah. We'll start on the sun. Like I said, I'm leaning towards the radio. I'll be in my office a couple hours before this on Wednesday in case you have last minute questions.